Hi, I'm Takahiro Sumi from Osaka University. Today I'm going to talk about how we can detect a free-floating planet by microlensing by introducing the result and analysis for the more data as a methodology. And then I'm going to briefly show the more recent result by the OGO collaboration. And then we're going to discuss about the future prospects. So what is the free-floating planet? So it is a planetary mass object that is not orbiting about any hot stars, and sometimes called the free-floating planet, rogue planet, orphaned planet, or interstellar planet. But can we call them a planet? That is still in debate, because if they formed around the hot star and scattered out from the orbit, then it can be called as a planet. But somebody says the definition of the planet should depend on the current status, not the origin. And if they form by the direct gas cloud collapse, like stars, they never been a planet. So we must call them as a planetary mass object or subground dwarfs. But there is no clear definition of such an object yet. So free-floating planetary mass objects have been found in many young star-forming regions by using the infrared deep imaging survey. So like this faint red object, they estimate, because even such a small object, when they are formed, they are still hot and emitting the infrared radiation. And they estimated the mass of such object of the mass of between the 5 and the 15 Jupiter masses. But there is such a large uncertainty in their such a photometric mass measurement and their abundance, because that rely on their estimated age and theory of the formation of such object. And it is not possible to measure such object in a field rather than this kind of young star-forming region. So this is some illustrate some idea of what object what we are talking about. So this is the size of the late M-type dwarfs, L brown dwarfs, T dwarfs, and Jupiters. They all have similar size. And this kind of free-floating planetary mass object is somewhere between these T dwarfs and Jupiter. So I think you already know the microlensing, so I'm going to skip this explanation. But this microlensing is predicted by Einstein in 1936, but he concluded it is impossible to measure such phenomena because the chance of such event is once in 1 million stars. But half century later, the Bogdan-Paczynski proposed the measurement of the microlensing survey. Just said watch the millions of stars to detect such a phenomenon. But this is very timely proposal, because around this era, the people start to use the CCD for observing the astronomical observation. Then that makes possible to such a massive observation. So here is the sensitivity of the various different methods of the exoplanet search. Black is the radial velocity, blue transit, and the magenta, the direct imaging, and red show the sensitivity of the microlensing and the current microlensing observation. And this purple indicates the future double first sensitivities. So the uniqueness of the microlensing is that did not rely on the flux from the hot stars. So the microlensing can probe the planetary object around the faint stars, like M dwarf or even brown dwarf. And also, the even microlensing can detect even without hot star. So it's like a free-floating planet. So as you can see, this sensitivity figure here, these are all for bound planets. And here, this region, double force can detect a free-floating object down to the mass. So more is the collaboration between Japan, New Zealand, and the United States. We are observing at the Mount John Observatory in the South Island of the New Zealand here. So as you can see, this is a very nice place to visit, although this is not the best place to do the astronomical observation because the thing is not great. So the Moa is named after the world's largest bird, which was in the New Zealand. The height was, they said, 3.5 meters, and the weight is 250 kilograms, and they couldn't fly. And, but unfortunately, they extinct 500 years ago. These Maori people, which came to the New Zealand from Polynesian islands thousands of years ago, and then they ate them, all of them. So I thought this picture was a real picture, but it can be because it's distinct kingdom. So we are using this 1.8 meter Moa 2 telescope, dedicated telescope, by using the camera with 10 CCD with the 80 megapixel. We have a very wide 2.2 square degree field of view, which is 10 times of the full moon. Thanks to this wide field of view, we can conduct very high cadence survey observation. So we are mostly observing towards the bulge. This is because the microlensing event rate is 10 to the minus 6. So it's very low. And furthermore, the detecting the planet is only the few percent of them. So we have to monitor the many stars by using the wide field. In addition, time scale of such object of the regular star is about 30 days, but the time scale of the Jupiter mass object is only a few days, and it's only a few hours for the Earth mass planet. So we also need a high cadence. To conduct such difficult requirement, we need a very wide field observation like our telescopes. So here is our observational field. This is the galactic center and the disk. So we are observing around 20 million stars in a 50 square degree field. So we are monitoring most of the field every 1 hour. And in this central region, we are observing every 10 minutes, which is very high cadence. And we are detecting about 600 events every year in real time and issuing the alert for prompting the follow-up observation. So our field is avoiding the high dust extinction region. So we are observing very dense field. So we are using the difference imaging analysis. This is the typical observed images. Most of the pixel is filled by the stars. Even most of the stars blended each other. So we take the best signal to noise image as a reference image, and then subtract this reference image from each observed image. Then we get this kind of subtracted image. So only the visible variable object is visible in this subtracted image, like this white spot and black spot. And then we measure these flags and create the light curves of them. And then we select the microlensing events among the other variable stars and any artifacts. So after rejecting the variable star, we still have some contamination for searching for the short microlensing event for the candidate as a free-floating planet. The one candidate is the wide separate binary event. So both the close and wide binary can mimic the short microlensing events. So all short events can be fit by the wide binary model because if the separation of the binary goes to very large, this can be as a single length event. And also the closed binary also create a very small planetary caustic, so that can mimic the short microlensing event. So here's an example. We found several binary looking short microlensing event like this. Here is the light curves of 2 years. The black is more data, and red is the overall data. Here is the data points from the one night. And as you can see, there is a very nice time asymmetric light curves. But if you see the tail, it rises very rapidly, and then for much rapidly than the regular single lensing microlensing event. And here is the residual. And we found this kind of caustic crossing event near the cusp approach of the planetary caustic. And we found this event can be explained by the wide separate binary with the planetary mass ratio of the 0.013. So this is just crossing the planetary caustic, but didn't cross near the primary. And another example is here. This is also the data points around one night. And it's short, very short, but it shows clear double horn, typical caustic crossing. And we found this event is crossing this caustic created by the brown dwarf mass ratio. Here is another case. Here is the data during the one night. And this can be explained by the closed binary with mass ratio of about 0.1. Here is the caustic. So we missed the caustic entrance, but we observed the exiting around the cusp. So there are other sources of the background in a short time scale microlensing event. The one significant background is the flare stars. Here is the data during the 2 years. We have two brightening episodes. So, they sometimes repeat during the observation, but the microlensing happened only the one time. And the light curve also looks different. They rise very rapidly, and then they fade more gradually, like this. So by the microlensing light curve fitting, we can discriminate from the microlensing. Another source of the background is the moving object, like the main belt asteroid, or sometimes the dust spot on a CCD. Because during the analysis, when we detect any new object on the image, we register the centroid, and then we conduct a photometry of all the images by fixed position. So if the object is moving, their measured flux changing in time symmetric, like this. So there looks like a very similar with microlensing, but it's not strictly the same as microlensing. So if we do the microlensing model fitting, we have an unphysical parameter for this event. So we check the microlensing parameter and also whether the centroid is moving during the event. Then we can discriminate with such object. So after we conduct such a lensing survey for the 2 years or more data, we found 474 events. And among them, the 10 events have a time scale is shorter than 2 days. So so you already know the only observable of the regular single lens event is the Einstein timescale, which is the Einstein radius divided by the transverse velocity. So this is proportional to the mass of the lens, square root of the mass, and this is typically about 20 days for the regular stars. And it can be the 1 day for the Jupiter mass lensing object. Here is one example. this is the light curve during the 2 years, and there's one brightening episode here. So here is the zoom up of the event. This bunch of the data points is based on the one night of the Moore observation. So as you can see, this event was magnified by the 30 during the one night. And here is the residual from the best fit. So best fit time, Einstein timescale is 1.2 days. So this is likely the Jupiter mass object. So here's another 2 examples of such a short event. The black is more data, red is ogle. So the time scale, so if you see this conceptual theme prepared by Jennifer and Kaylin, that's the table 4 and 5 show the typical Einstein timescale for the various mass and distance of the lens. So if you see this table 4, which shows for the case of the bulge lenses, if you see the distance of the 6 kiloparsec, the Einstein timescale is about 30 days for the 0.3 solar mass M dwarfs, and it's 16 days for the 0.1 M dwarfs, and 5 days for the brown dwarfs, and 1.7 days for the Jupiter mass. And for the disk size, it is about 1 day for the Jupiter mass object. So these kind of short events is very likely the Jupiter mass object. So here is but as I said, all the physical parameter is degenerate in a time scale. So we cannot say this is really the planetary mass object by the single individual event. So we have to do some statistics by using the timescale distribution. So this is the observed timescale distribution of the total 474 events. And this is a timescale in the log scale. And this dashed line is the model distribution predicted by the known object. So we found some excess around the short timescale less than 2 days. So we wanted to, what's the reason of this, some excess for the short events. So we'd like to model the timescale distribution to know what's the mass is causing such a distribution. So Einstein timescale TE is the only observable in the regular single lens microlensing event, and given by this equation. But this is in the mass, distance, and transverse velocity is degenerate. So we can model this timescale distribution by calculating, by using the Monte Carlo simulation, assuming the mass function and the galactic mass density to define this distance, and assuming the velocity model for simulating this transverse velocity. So for each given mass function model, we can create the model timescale distribution by using the standard model of the galaxy. So for the mass function, we assume the 2 types of the model. So first, the heavy stars more than the 1 solar mass, we assume the salpeter-like slope, initial mass function, and assume they evolve to the stellar remnant. And for the stars less than the 1 solar mass, we took 2 models. The one is the broken power law, like this, and the other is the Chabrier's log normal mass function. So for the broken power law, we assumed about the slope is -2 for larger than the 0.7 solar mass, and minus 1.3 for between the 0.8 to the 0.7 solar mass. And we fitted the slope for the brown dwarf regime, and we found the slope is minus 0.5. And then this is the final mass function. And for the log normal mass function, we used the average of the 0.12 solar mass, and sigma is 0.76. So this is the resultant mass function. It looks quite similar. And for the short time scale event, we assumed, we adopted delta function mass function. We don't think these population are delta function, but we don't have any mass resolution, and so we assume the most simple mass function. Because we have a very little mass resolution, because the real mass distribution is diffused by the the various velocity dispersion and so on. So we conducted an image level simulation to detect the detection efficiency, and then here is the final detection efficiency. And time scale, we have a very low but still significant time scale around here. And here is the final best fit model. So this region is based on the black hole lens and neutron star, white dwarf, and the main sequence stars. And brown dwarf contribute around this region. And here we can fit the planetary mass object. And our best fit, we conduct likelihood analysis for measure the best model for the planetary mass object. We found about the number of the planets is 1.8 times the number of the main sequence stars. But as you know, the error bar is very large. It's about so within the 2 sigma level, this can be about 20% of the main sequence stars. And also the mass of the planet, the uncertainty is very large. It can be about a sub-brown dwarf, and it can be about Neptune mass. So we also try to model the power of mass function for the planetary mass object, and predicting about 5 times the main sequence stars. But we cannot distinguish from the delta mass function. So here is the OGO recent result based on the 4,000 microlensing event. This red line shows the best model by our analysis, and it shows the indicating the mass, Jupiter mass object is about 5% of the main sequence stars, and or at least less than a quarter of the main sequence stars. And they also find ultra short, about 0.2 days microlensing event like this, and then they suggest there exists a super Earth or Earth mass free floating planet. And the difference may be mostly explained by the small number of the statistics in the previous analysis, and some contamination from the other time scale due to the uncertainty of the TE, and also the contamination from the short binary events. And we don't know where they, because we don't know the distance. And I'm going to skip this. And most of the such prediction for these kind of free-floating objects can be created by the scattering of the interaction between the planets. Their simulation, they starting from the 6 planets, and after the several millions of years, most of them are scattered out. And Ma and Mao and all, they did some simulation using the population census by the Ida and the Lin, and then simulate how many planets are scattered out. And here is the timescale distribution due to the host, and here is the timescale distribution by the scattered planets. And then that can be explained the short timescale events which OGO found. So to understand the nature of such free-floating planet, we need more accurate mass function measurement, and WFOS can do such a job. Because WFOS have a very high sensitivity on the free-floating region, and here is a simulation for the free-floating planets for the Mars mass. WFOS can measure about 2,000 free-floating planets down to the Mars mass. And also, before the WFOS, we are trying to do the infrared microlensing experiment toward the barge at building the 1.8 meter telescope at SAO. We're going to have a 1.5 square degree field of view in infrared and conduct an H-band microlensing survey. In the H-band, we can measure the more central region of the galactic center and where the stellar density is much higher, so we can detect more events and more planets. And also, we can measure the planet frequency at the galactic center. So the stellar number density is different, and the metallicity may be different from the other region we are observing in the optical. So we can compare the planetary abundance in different environments, which might be interesting. And after this observation, we can use selecting the WFOS observational field, and we can so this is the proposed observational field. This color map indicates the map of the microlensing event measured by Moore. So the red region is higher, and the event rate is higher near the galactic center. The WFOS is going to observe around here, but fluctuation is larger in local. So we're going to map the event rate around this region and then optimize the field the WFOS is going to observe to maximize the yield of the WFOS. And also, after launch, we're going to conduct a simultaneous observation from the ground and the space. Because it's infrared, our telescope can only conduct such a simultaneous observation. And that is similar with observation by Spitzer and ground. So if you go back to this conceptual theme, they predict showing the projected timescale distribution. And Jupiter mass object it is about 0.2 AU. So considering the separation of the Earth and the L2, we are more sensitive to the space-based parallax for the small mass object, like this object. So we prime, and the WFOS can constrain the mass of the FF free-floating planet. Okay, I'm going to stop here. Yeah, it's quite similar. Mm-hmm. Yes.
10%, 20%, and how much more efficient were they?
Well, comparing that, it's not that different. It's quite similar. So from the direct imaging, we have a constraint on the existence of the wide separate planets. And from the Lafreniere, they set a strong upper limit of such object between the 10 to about 100, 500 AU, about 40%. And more recent measurements, these people have a constraint about such wide separate planets can be less than 10% or 16% between the 1 to 13 Jupiter mass, between the 10 to 100 AU. So if the best overall result, which showed about 5% of the such a free-floating planets, so if that's all the such wide separate planet can be explained by such wide separate planets. But these the observation are only the upper limit. They don't say existing. So they can be all bound, but it's not necessarily. And this simulation by the Ma and Mao, these regional prediction, the mass based on the mass of the Earth and the super Earth, and this region based on the Jupiter mass object. So there's still a chance to exist such object. Well, the Ogo paper says they only selected, they can constrain the blending and timescale well, and they all rejected with Harvard degeneracy. And that is similar with what we did. And if we have a good coverage around the tail of the microlensing event, we can constrain the timescale and the blending pretty well.
Takahiro again.
Thank you.